In the early 20th century, chemistry was undergoing a quiet transformation. Scientists could identify elements, combine them into compounds, and describe reactions with increasing precision. Yet something essential remained unclear. They could see what substances did, but not fully understand why they behaved the way they did. The structure of molecules, the way atoms bonded together, and the forces that held them in place were still only partially understood. Chemistry, in many ways, was descriptive rather than deeply explanatory. It was within this shifting landscape that Linus Pauling emerged, a scientist who would not only study molecules, but reveal the underlying principles that govern their structure and behavior. Linus Pauling was born in 1901 in Portland, Oregon, into a family that faced financial difficulty after the early death of his father. His childhood was marked by limited resources, but also by a strong sense of independence and curiosity. From a young age, Pauling showed an intense interest in science, particularly chemistry. He would conduct small experiments on his own, collecting materials and trying to understand how substances interacted. This early curiosity developed into a focused ambition. Pauling pursued his education at Oregon Agricultural College, where he studied chemical engineering. During this time, he began to see chemistry not just as a practical discipline, but as a field filled with deeper questions about the nature of matter. He was particularly interested in how atoms come together to form molecules, and how these structures determine the properties of substances. After completing his studies, Pauling moved to the California Institute of Technology, where his scientific career truly began to take shape. At Caltech, he entered an environment that encouraged both experimental work and theoretical thinking. It was here that Pauling encountered the emerging field of quantum mechanics, a new framework for understanding the behavior of particles at the atomic level. Quantum theory was still developing, but it offered powerful tools for explaining phenomena that classical physics could not fully describe. Pauling recognized its potential immediately. He saw that quantum mechanics could provide the key to understanding chemical bonds, the connections that hold atoms together in molecules. Until then, bonding had been described in relatively simple terms, often based on empirical observations rather than fundamental principles. Pauling set out to change that. He began combining ideas from physics and chemistry, using quantum theory to explain how electrons are arranged around atoms and how they interact to form bonds. One of his most important contributions was the concept of hybridization. He proposed that atomic orbitals, the regions where electrons are likely to be found, can combine to form new shapes that better explain the geometry of molecules. This idea helped clarify why certain molecules have specific structures, such as the tetrahedral shape of methane. This was more than a technical detail. It provided a clear link between the abstract mathematics of quantum mechanics and the physical shapes of real molecules. Chemists could now understand not just what molecules looked like, but why they took those forms. Pauling also introduced the concept of electronegativity, a way of describing how strongly an atom attracts electrons in a bond. By assigning values to different elements, he created a scale that allowed scientists to predict the nature of chemical bonds. Some bonds would be more ionic, involving a transfer of electrons, while others would be more covalent, involving shared electrons. This framework brought order and predictability to chemical behavior, making it easier to understand reactions and properties. His work on chemical bonding was brought together in his influential book, The Nature of a Chemical Bond. This book became one of the most important texts in chemistry, shaping how the subject was taught and understood for decades. It did not simply present facts. It provided a unified framework, showing how atomic structure, electron behavior, and molecular geometry are all connected. Pauling's approach was distinctive. He was not content with isolated discoveries. He sought to build systems of understanding, connecting ideas across different areas of science. His work demonstrated that chemistry could be explained through fundamental physical principles, bringing a new level of depth and clarity to the field. At the same time, Pauling was not limited to theoretical work. He engaged in experimental research, using techniques such as X-ray crystallography to study the structure of molecules. By analyzing how X-rays scatter when passing through a crystal, scientists can determine the arrangement of atoms within it. Pauling used this method to confirm and refine his ideas about molecular structure, linking theory with direct observation. His work extended into biology as well. He became interested in the structure of proteins, the complex molecules that play essential roles in living organisms. By applying his understanding of chemical bonds and molecular geometry, he helped uncover the alpha helix, a common structural pattern in proteins. This discovery showed how biological structures could be understood through the same principles that govern simple molecules. What made Pauling's work especially significant was its breadth. He moved between disciplines, connecting chemistry, physics, and biology in ways that had not been done before. He demonstrated that the same fundamental principles apply across different scales, from simple molecules to complex biological systems. By the time his early career had matured, Pauling had already transformed chemistry. He had turned it from a largely descriptive science into one grounded in deep theoretical understanding. The invisible world of atoms and bonds was no longer mysterious in the same way. It had become something that could be described, predicted, and visualized with clarity. And this was only the beginning of a career that would extend far beyond the laboratory, into areas that would shape not just science, but global society itself. As Linus Pauling's work on chemical bonding began to spread through the scientific world, its influence was immediate and far-reaching. Chemists who had once relied on observation and empirical rules now had access to a deeper framework that explained why molecules formed the way they did. His ideas did not remain confined to theory. They became practical tools, allowing scientists to predict molecular shapes, understand reactivity, and design new compounds with a level of confidence that had not previously been possible. At the California Institute of Technology, Pauling became a central figure in shaping modern chemistry. His laboratory was not just a place of research, but a place where new ways of thinking were developed and shared. Students and collaborators worked closely with him, absorbing his approach to science, one that combined rigorous logic with imaginative insight. He encouraged bold questions, often pushing beyond established boundaries, seeking connections between different areas of knowledge. Pauling's thinking was driven by a desire for unity. He did not see chemistry as isolated from physics or biology. Instead, he believed that all of these fields were connected through underlying principles. The behavior of electrons, described by quantum mechanics, determined how atoms bond. Those bonds, in turn, determine the structure of molecules. And molecular structure shaped the behavior of living systems. This chain of reasoning allowed him to move across disciplines, applying similar ideas in different contexts. One of the most significant directions his work took during this period was the study of biological molecules. Proteins, which are essential to nearly every function in living organisms, were still poorly understood at the structural level. Scientists knew their chemical composition, but not how their atoms were arranged in three-dimensional space. Pauling recognized that understanding protein structure would require the same principles he had developed for simple molecules. Using both theoretical reasoning and experimental data, he proposed that proteins could form regular, repeating structures. One of these structures, which he described in detail, became known as the alpha helix. In this arrangement, the protein chain coils into a spiral, stabilized by hydrogen bonds between different parts of the molecule. This concept was a major step forward, providing a clear and testable model for how proteins could be organized. The importance of this discovery extended beyond chemistry. It showed that the complex structures found in living systems could be understood through fundamental physical and chemical principles. Biology was not separate from the rest of science. It followed the same rules, even if the systems involved were more intricate. At the same time, Pauling continued refining his work on chemical bonds. He explored the nature of resonance, a concept used to describe situations where a single, fixed structure is not sufficient to represent a molecule. Instead, the true structure is a combination of multiple possible arrangements. This idea helped explain the stability of certain molecules that could not be fully understood using simpler bonding models. Resonance was another example of Pauling's ability to think beyond rigid frameworks. He recognized that reality at the atomic level is not always easily captured by a single picture. Sometimes, multiple perspectives are needed to describe the true behavior of a system. This flexible way of thinking allowed him to address problems that resisted simpler explanations. During this period, Pauling also became known for his ability to communicate complex ideas clearly. His lectures and writings made advanced concepts accessible to a wider audience, helping to spread the new understanding of chemistry across the scientific community. His book, The Nature of the Chemical Bond, continued to influence generations of students and researchers, becoming a foundational text in the field. As his reputation grew, so did the recognition of his work. In 1954, Pauling was awarded the Nobel Prize in Chemistry for his research into the nature of the chemical bond and its application to understanding the structure of complex substances. This honor reflected not only the importance of his discoveries, but also their broad impact across multiple areas of science. Yet Pauling's career was not defined solely by scientific achievement. He began to engage more deeply with social and political issues, particularly those related to science and its consequences. The development of nuclear weapons during and after the Second World War raised serious concerns about the role of scientists in society. Pauling became increasingly aware that scientific knowledge could be used in ways that had both constructive and destructive outcomes. He chose to take a public stance. Pauling became an advocate for nuclear disarmament, speaking out against the testing and use of nuclear weapons. He argued that the dangers posed by these weapons extended beyond immediate destruction, affecting the environment and human health through radioactive fallout. His position was based not only on moral concerns, but also on scientific evidence, which he presented in a clear and direct manner. This shift in focus brought both support and criticism. While many admired his willingness to address global issues, others viewed his activism as controversial, particularly during a time of political tension. Pauling faced opposition, including challenges to his views and scrutiny of his activities. Despite this, he continued to speak out, maintaining his commitment to what he believed was necessary for the safety of humanity. In 1962, his efforts were recognized with a Nobel Peace Prize. This made him one of the few individuals to receive 2 Nobel Prizes and the only person to receive them in different fields without sharing the award. It reflected the dual nature of his career, combining scientific excellence with a broader concern for human welfare. Through all of this, Pauling maintained a consistent approach. Whether working on chemical bonds or global issues, he relied on evidence, reasoning, and a willingness to challenge established ideas. He did not separate science from the world around it. Instead, he saw it as deeply connected to human life, carrying both opportunities and responsibilities. By the middle of his career, Linus Pauling had already achieved more than most scientists could hope for. He had transformed chemistry, contributed to biology, and entered the global conversation about science and its impact on society. Yet his work and influence were still continuing, moving into new areas that would further shape both scientific understanding and public thought. As Linus Pauling moved into the later decades of his career, his work began to take on an even broader scope, extending beyond the traditional boundaries of chemistry and into questions of health, medicine, and human well-being. While many scientists focused deeply on a single area, Pauling continued to expand outward, guided by the same principle that had shaped his earlier work, the belief that underlying patterns connect different aspects of the natural world. After his groundbreaking contributions to chemical bonding and protein structure, Pauling became increasingly interested in how molecular processes affect human health. He began to explore the idea that the behavior of molecules within the body could explain both disease and wellness. This approach was consistent with his earlier work. Just as he had used chemistry to understand biological structures, he now sought to use it to understand biological function and dysfunction. One of his most well-known and debated areas of interest was his work on vitamins, particularly vitamin C. Pauling proposed that high doses of vitamin C could have significant health benefits, including strengthening the immune system and potentially helping to prevent or treat certain illnesses. He believed that modern diets and lifestyles might not provide sufficient amounts of certain nutrients, and that supplementation could play an important role in maintaining health. This idea gained widespread public attention. Many people were drawn to the possibility that something as simple as a vitamin could have powerful effects on health. Pauling wrote books and gave lectures on the subject, presenting his views in a way that was accessible to a general audience. His reputation as a leading scientist gave weight to his claims, bringing the topic into mainstream discussion. However, this area of his work also became controversial. While some studies suggested potential benefits of vitamin C, others did not support the same conclusions, particularly regarding its use in treating serious diseases such as cancer. The scientific community remained divided, with ongoing research attempting to clarify the effects of high-dose vitamin supplementation. Pauling's position was often seen as ahead of the available evidence, and it led to debates about the balance between scientific innovation and caution. This period of his career highlights an important aspect of scientific work. Even highly respected scientists can propose ideas that are later questioned or refined. Progress is not always linear, and new hypotheses must be tested, challenged, and sometimes revised. Pauling's willingness to explore unconventional ideas reflected his broader approach, but it also exposed him to criticism from those who believed his conclusions went beyond what the data could support. Despite these debates, Pauling remained active and engaged. He continued writing, researching, and participating in scientific discussions. His interest in health led him to establish the field he called orthomolecular medicine, which focused on the role of molecules in maintaining optimal health. While this field has not been fully accepted within mainstream medicine, it contributed to ongoing conversations about nutrition, supplementation, and preventive care. At the same time, his earlier contributions continued to influence science. The principles he had developed for understanding chemical bonds remained central to chemistry education and research. His work on protein structures contributed to the growing field of molecular biology, which was expanding rapidly with new discoveries about DNA and genetic processes. Even as science moved forward, Pauling's ideas remained part of its foundation. His role as a public figure also continued. Pauling was known not only within scientific circles, but also among the general public. His advocacy for nuclear disarmament, combined with his later work on health, made him a visible and sometimes controversial voice. He demonstrated that scientists could engage with society, addressing issues that extend beyond the laboratory. Throughout these years, Pauling maintained a consistent intellectual style. He approached problems with confidence, often trusting his intuition as well as his analytical reasoning. This approach had served him well in his earlier work, allowing him to make bold connections that others had not seen. In later years, it sometimes led him into areas where the evidence was less clear, but it also reflected his willingness to explore new ideas rather than remain confined to established paths. His career, taken as a whole, shows both the strengths and complexities of scientific inquiry. Great advances often come from individuals who are willing to think differently, to question assumptions, and to pursue ideas with persistence. At the same time, the process of science requires careful testing and validation, ensuring that ideas are supported by evidence. Pauling's work illustrates both sides of this process, from widely accepted breakthroughs to more debated contributions. As the 20th century progressed, the world of science continued to evolve, building on the foundations laid by earlier generations. New technologies allowed for deeper exploration of molecular structures, genetic information, and biological systems. In many of these developments, the influence of Pauling's ideas could still be seen, shaping the way scientists approached complex problems. Linus Pauling remained a figure of lasting importance. He had helped transform chemistry into a more precise and predictive science, contributed to the understanding of biological structures, and engaged with broader questions about health and society. His work spanned multiple fields, reflecting a belief that knowledge is interconnected and that understanding in one area can illuminate another. Even as debates continued around some of his later ideas, the impact of his earlier discoveries remained clear. They had changed how scientists think about atoms, molecules, and the structures that make up the natural world. And through that understanding, they had helped reveal the deeper patterns that connect matter, life, and the processes that sustain them. As Linus Pauling entered the final years of his life, his legacy had already become deeply embedded in the foundations of modern science. The fields he had helped shape, from quantum chemistry to molecular biology, continued to expand in ways that reflected the principles he had introduced decades earlier. What made Pauling's career remarkable was not only the range of his contributions, but the way those contributions connected different domains of knowledge into a coherent understanding of the natural world. By this time, chemistry had been permanently transformed. The idea that the behavior of substances could be explained through the arrangement and interaction of electrons was no longer new or controversial. It had become standard. Students learned about hybridization, electronegativity, and molecular structure as essential concepts, often without realizing that these ideas had once been uncertain and debated. Pauling's work had shifted chemistry from a largely descriptive science into one grounded in fundamental principles that could predict and explain behavior with precision. His influence on biology was equally significant. The understanding of protein structures, including the alpha helix, became a stepping stone for further discoveries in molecular biology. As scientists began to explore DNA, genetic coding, and cellular processes, the importance of molecular shape and bonding became increasingly clear. Pauling's approach, applying chemical reasoning to biological systems, helped establish a framework that would later support advances in genetics, biotechnology, and medicine. Even in areas where his later ideas remained controversial, his impact was undeniable. His advocacy for nutritional science, particularly his emphasis on vitamins, sparked widespread discussion about the relationship between diet and health. While not all of his claims were accepted, they contributed to a broader awareness of how lifestyle and nutrition influence well-being. In this way, his work extended beyond the laboratory into everyday life, encouraging people to think more carefully about the factors that affect their health. Pauling's role as a public intellectual remained strong. He continued to speak and write about issues related to science and society, emphasizing the responsibility that comes with knowledge. His earlier efforts to promote nuclear disarmament had already demonstrated his willingness to take positions on global issues. In his later years, this perspective remained consistent. He believed that scientific understanding should not be isolated from human concerns, but should instead be used to improve the world. Throughout his life, Pauling received numerous honors and recognitions. Among them, his 2 Nobel Prizes stood as clear markers of his influence, one for his contributions to chemistry and the other for his efforts toward peace. This combination reflected the dual nature of his work, bridging the gap between scientific discovery and social responsibility. It was rare for a scientist to have such a broad impact, and Pauling's career remained an example of how intellectual work can extend beyond its original field. Despite his achievements, Pauling's journey was not without complexity. He experienced both admiration and criticism, particularly in relation to his later ideas about health. This mixture of responses highlights an important aspect of scientific life. Influence and recognition do not place a person beyond debate. Instead, they often bring greater scrutiny as ideas are examined, tested, and discussed within the broader community. Pauling's ability to continue working and engaging with new ideas, even in the face of criticism, reflected his enduring commitment to inquiry. He did not retreat from difficult questions. Instead, he continued exploring them, guided by the same curiosity that had shaped his early career. This persistence, combined with his willingness to cross disciplinary boundaries, defined much of his life's work. Linus Pauling died in 1994 at the age of 93. By the time of his death, the scientific world had changed in ways that would have been difficult to imagine at the beginning of his career. Advances in molecular biology, chemistry, and medicine had created new possibilities for understanding and manipulating the natural world. Many of these advances were built on concepts that Pauling had helped establish. His legacy can be seen in both the details and the larger picture. In the details, his theories continue to be taught, used, and refined. In the larger picture, his approach to science, seeking connections, building unified explanations, and applying knowledge across fields, remains influential. He showed that understanding does not come from isolated facts, but from seeing how those facts fit together into a broader system. The story of Linus Pauling is not only about discovery, but about perspective. It is about the ability to look at familiar problems in new ways, to connect ideas that others see as separate, and to pursue understanding with both depth and breadth. His work reminds us that science is not a collection of disconnected results, but a continuous effort to reveal the patterns that underlie the world around us. From the structure of a simple molecule to the complexities of human health and global responsibility, Pauling's influence extends across scales and disciplines. And in that wide-ranging impact, his life reflects the power of curiosity guided by reason, shaping not only knowledge, but the way that knowledge is used. By the time Linus Pauling's life work had fully settled into the foundation of modern science, the world had already begun moving into an era that depended on his ideas in ways that were almost invisible to the public. The language he helped create for understanding molecules, bonds, and structure became so deeply integrated into education and research that it no longer felt new. It became the default way of thinking. Generations of scientists were trained not to question these principles, but to use them, extend them, and build upon them. In that sense, Pauling did something few individuals achieve. He did not just contribute to science. He changed the way science itself is done. One of the clearest reflections of this influence can be seen in how modern researchers approach problems at the molecular level. Instead of relying on trial and error, scientists now begin with prediction. They map out how atoms will interact, how electrons will distribute themselves, and how those interactions will shape the behavior of a substance. This predictive power is not perfect, but it is powerful enough to guide entire industries. Whether developing new medicines, creating stronger materials, or designing more efficient energy systems, the process often begins with principles that Pauling helped clarify. In medicine, this shift has been especially significant. There was a time when treatments were discovered largely by observation, by testing substances and seeing what worked. Today, many drugs are designed with intention. Scientists study the structure of a disease at the molecular level, identify specific targets within the body, and then design compounds that interact with those targets in precise ways. This approach reduces uncertainty and increases effectiveness, turning medicine into a more exact science. This transformation can be traced back, in part, to the idea that structure determines function. It is a simple statement, but it carries enormous weight. The shape of a molecule determines how it behaves, how it interacts, and what role it can play. Pauling helped make this idea central to scientific thinking, and its influence continues to expand as tools become more advanced. At the same time, the technological world has begun to operate on principles that depend on molecular understanding. Electronics, for example, rely on materials whose properties are controlled at the atomic level. The behavior of semiconductors, the materials that power modern computers and communication systems, depends on how atoms are arranged and how electrons move through those structures. Even though Pauling did not directly work in this field, the framework he helped establish made it possible to understand and refine these materials. In more recent years, entirely new fields have emerged that extend these ideas further. Nanotechnology, for instance, focuses on building structures at the scale of individual atoms and molecules. Scientists in this field design systems with specific properties, creating materials that can respond to their environment, deliver drugs within the body, or perform highly specialized functions. This level of control would not be possible without a deep understanding of chemical bonding and molecular structure. Artificial intelligence has also entered this space, accelerating the pace of discovery. Algorithms can now analyze vast amounts of data, predict molecular interactions, and suggest new compounds that might have useful properties. This combination of computational power and chemical understanding is reshaping how research is conducted. Yet, even as the tools become more advanced, the underlying principles remain rooted in the ideas Pauling helped develop. His influence, however, is not limited to technical progress. Pauling's life also raises important questions about the role of scientists in society. He did not remain confined to the laboratory. He stepped into public debates, spoke about global risks, and used his voice to advocate for change. This decision was not without consequence. He faced criticism, political pressure, and resistance, particularly during times when his views were seen as controversial. But his actions reflected a belief that knowledge carries responsibility. He understood that scientific discoveries do not exist in isolation. They shape the world, influence policy, and affect the lives of millions. By engaging with these broader issues, Pauling demonstrated that scientists can play a role beyond research, contributing to discussions about how knowledge should be used. This aspect of his legacy remains highly relevant. Today, scientists are often called upon to address issues such as climate change, public health, and emerging technologies. The expectation that they will not only discover, but also communicate and guide reflects a shift in how science is viewed. Pauling was part of this shift, showing that expertise can and sometimes must extend into the public sphere. At the same time, his later work serves as a reminder of the need for balance. His strong advocacy for certain health ideas, particularly related to vitamin C, demonstrated how conviction can sometimes move ahead of consensus. While his intentions were rooted in improving human health, the debates that followed highlighted the importance of rigorous testing and careful interpretation of evidence. This dual aspect of his career, groundbreaking success alongside controversial positions, makes his story more complete and more human. It shows that science is not only about results, but about judgment, interpretation, and the constant process of refinement. Even the most brilliant minds operate within uncertainty, navigating between insight and evidence, between possibility and proof. As time moves forward, the world continues to build on the foundations Pauling helped establish. New discoveries in genetics, molecular engineering, and advanced materials all carry traces of his influence. The ability to manipulate matter at increasingly smaller scales, to design systems with specific functions, and to understand complex biological processes all depend on the conceptual tools he helped create. Yet perhaps the most enduring part of his legacy is not any single idea, but a way of seeing. Pauling approached science as a connected system, where understanding in one area could illuminate another. He looked for patterns, for underlying principles, for the deeper logic that ties different phenomena together. This perspective remains one of the most powerful tools in science, guiding researchers as they explore increasingly complex problems. His life reflects a continuous movement between discovery and application, between theory and practice, between science and society. From a structure of a simple chemical bond to the broader implications of scientific knowledge, Pauling's work spans a range that few have matched. In the end, Linus Pauling's story is not only about what he discovered, but about how those discoveries continue to shape the world.